Let's have another look at the diagnostic possibilities of Wireshark. The point is to detect a situation when someone tries to send a large amount of data. We'll try out the data visualization capabilities of Wireshark. To evaluate the contents of the file, let's try to visualize them first. We look at the I/O graphs from the Statistics menu. The image shown below is a graphical representation of units called packet tick. The unit is not really intuitive. We can change it into bytes tick. Now we see at what speed data is transmitted at a given point in time. We see how the speed with which anyone sent or received data changed over time. It's presented as a summary. Looking at the statistics, we can notice that one of the computers who tried to establish a connection was identified by the address 10.0.52.164. This information can be included in the graph. It turns out that we can visualize a variety of information on the graph. After we've created a red graph representing a new rule, we can change the graph style to impulses. We can make the graphs overlapped based on the filters previously created in Wireshark. If we look at the example again, you should notice that the client downloaded data from two different servers. And in one case, the bandwidth was small, but in the other, much bigger. In this example, we're focusing on data visualization in Wireshark. Let's see another problem, namely the case before what happens if Wireshark is not able to properly interpret the data. Examining the above capture file, you'd conclude that this is a NetBIOS over TCP/IP session. Looking closely at the data presented by Wireshark, it turns out that the program does not interpret the data as SMB. It shows raw data. This is an example of a situation in which someone uses a protocol that utilizes the TCP transport that Wireshark is not familiar with, or someone has changed the destination port, and Wireshark decodes the wrong data. What should we do in this case? First, we'll try to decode it. If you suspect what could really have happened, select any packet with the right mouse button and choose Decode As. From the list, you can choose the protocol that you suspect was used. Let's try to decode data as FTP. After applying the decoder, the situation looks better right away. We have a correct interpretation. We can now track the selected packet by using the Follow TCP Stream from the right mouse button click menu. It turned out that it was actually a TCP session. We can see who connected to which server and what folders they browsed through. If, in the main Wireshark window, under the subheading Data, there's not information about the protocol, try decoding it as a different protocol. This operation almost always succeeds. Shortly, we'll look at another capture file. It'll be the record of a process which we mentioned in one of the earlier lectures. We talked about how you can make a switch act like a hub. We said that this can be done by sending a large number of IP addresses associated with a random MAC address. This is the situation you see on the screen. Please note how quickly the packets were sent, and how many hosts were apparently involved in the communication. Here we see only the SYN packets of the TCP protocol. There are no data in these packets, so it's not an unusual thing. Please note that the window size field value is set to 512. No operating system uses such a small TCP initial window size. The SYN packet gives no reason to set the window size smaller than the default one, because we haven't received any data yet. A situation where there's only SYN packets and the window size is 512 seems readily suspicious. So really, this is a signature of MacOff, a program used for switch flooding. If you make a coloring rule for the window size value 512, this is the first part you should have in your filter. At this point, we can get some false positives. From time to time, computers can inform you about such window sizes. We're halfway to solution. We should now move the coloring rule to the top. So far, the rule works as it should. We'll add just one more detail to it. That should be a SYN packet. This is the final rule which we would like to add to our existing coloring rules. Thus, we have worked out the signature of MacOff. If we manage to do this with one program used for automated attacks on operating systems and computer networks, we'll probably manage with others as well. Let's try it out on another demonstration file. We'll open the file named Nessus. The file name suggests what we'll be looking for. Here, we mostly want to get to know another Wireshark functionality. Press Ctrl+L to open the Find window. We can now search for something by display filters. That is, all rules that could be entered into the program by hexadecimal values. They're displayed in the lowest window of the program, or by strings, typing any string of characters. These criteria will be used to search the packets list, the details pane, or the bytes pane. Let's see what happens if you type the expression Nessus. We found the program, which, as we mentioned in the previous lectures, tries to be neither discreet nor stealthy. Nessus is a program that detects certain errors and vulnerabilities in the configuration of network services. The program probes remote services. In packets sent by Nessus, we find program names. We could create another coloring rule or another filter that will show whether someone in the company uses Nessus.